Greetings and welcome to the 7th episode of PHS Physics SOS. Today I'm going to be covering the forces worksheet, which is on material from the first part of chapter 4. And we're going to start with the first problem, which says a 60-kilogram astronaut weighs 96 newtons on the surface of the moon. The acceleration due to gravity on the moon is... Okay, so if we have a 60-kilogram astronaut, weighs 96 newtons... 96 newton. Normal force of 96 newtons. That's not really important, though. It's just balancing the free body diagram. This wants to know what his acceleration is, so we just use F equals ma. We know that our force is 96 newtons, equals our mass, which is 60 kilograms, times our acceleration, which is our unknown. So we take 96 newtons divided by 60 kilograms, and we get our acceleration, which when you plug it into your calculator is 1.6 meters per second squared. The next question says, which graph best represents the motion of an object that has no unbalanced forces on it? So, and it has a graph like this. This is momentum versus time. Graph like this is acceleration versus time. Graph like this, velocity versus time, and a graph like this, displacement versus time. So, no unbalanced forces means the net force equals 0, and since the net force equals mass times net acceleration, and this equals 0, then our, since mass isn't equal to 0, that means our net acceleration has to equal 0. And when you have 0 acceleration, your velocity is a constant. So already it can't be this, because this has an increasing acceleration. It can't be this, because the velocity isn't a constant. We don't even know what momentum is yet, so ignore that. So it has to be this, because if you have a constant velocity, you're going to have an increasing displacement. So this is d. Oh, and the first one, this was A. The next question is question 3, which says a force of 100 newtons is applied to an object at an angle of 30 degrees from the horizontal, as shown in the diagram below. What is the magnitude of the vertical component of this force? Okay, so the diagram looks like this. So we've got some object over here, and this is 30 degrees, and this is 100 newtons. And it wants to know the vertical force. So to figure out the vertical force, we have an angle and the hypotenuse. So we do it the same way that you separated velocity into its component parts when we did projectile motion, which is by using trigonometry. So to relate these three values, we have an angle and we have its opposite side and the hypotenuse. So the trigonometric identity that relates an angle, its opposite side, and the hypotenuse is sine. So sine of 30 degrees is going to equal the vertical force over the hypotenuse, or the force on the hypotenuse, so it's 100 newtons. So 100 sine 30 equals our vertical force. And when you plug that into your calculator, you get sine 30 is 0.5, so you get 100 times 0.5 equals 50 newtons. And that is D. The next question is question 4, which says the handle of a lawn roller is held 45 degrees from the horizontal. A force F of 28.0 newtons is applied to the handle of the roller. Applied to the handle of the roller is pushed across a level lawn as shown in the diagram below. So we've got, and I can't draw circles, but whatever. And this is our force, which is 28 newtons. And it wants to know, oh, and then the question says, what is the magnitude of the force moving the roller forward? So if you have a force like this, and you split it up into a vertical and horizontal component, the vertical component is pushing it downwards. So that's not moving it forward. It's the horizontal component that's moving the roller forward. So we need to find the horizontal component of this vector. So we have 45 degrees, 28 newtons, and we want the horizontal force. So we want our trigonometric identity, which relates to those three values. That's going to be the cosine of 45 degrees. It's going to be equal to our horizontal force over our hypotenuse. Multiplied over. And if you plug it into your calculator, you're going to get 19.8 newtons, which is C. The next question is question 5, which reads, the diagram below represents a constant force F acting on a box located on a frictionless horizontal surface. As the angle theta between the force and the horizontal increases, the acceleration of the box will. Okay. Let's draw our diagram real quick. So, the acceleration of the box is going to increase. Since the box is moving horizontally, the acceleration of the box is going to increase the most when the horizontal force is the most. So when this force, the biggest part of it is in the horizontal direction as opposed to the vertical direction. So to maximize how much of the force is in the horizontal direction, we want it all in the horizontal direction. In other words, we want the angle to be the least. If we put the force like this, going straight up, none of it is going to be in the horizontal direction. It's not going to be accelerating at all. So as the angle increases, so as it goes from 0 higher and higher and higher up to 90, the acceleration of the box is going to decrease because the horizontal component of this force, for example, if we have it like this with a big angle, there's only going to be a little bit in the horizontal direction and a lot, sorry, this should be F, and a lot in the vertical direction. But if we have a very small angle, we're going to have most of our force in the x direction, or the horizontal direction, and very little of it going up. So the answer is going to be B. As the angle gets bigger, this is going to decrease, thus causing a lower acceleration of the box and or lower horizontal force, and thus lower horizontal acceleration. Next question is question 6, and it says, in the diagram below, the weight of a box on a plane inclined at 30 degrees is represented by the vector W. What is the magnitude of the component of the weight W that acts parallel to the incline? Okay. So it wants to know what sorry, that's completely wrong. This is W. W is going straight down. And it says, what is the magnitude of the component of the weight that acts parallel to the incline? Okay, so if we turn this 90 degrees, or not 90 degrees, 30 degrees, I guess. Now it looks like this weight is at an angle, and straight up and down, you know, let me redraw this. So if we hold this at an angle, where this plane looks like it's flat, then we can split this up into two components. We can split the weight up into a component that's parallel to the plane and perpendicular to the plane. And the way we do that is using this angle over here. So this angle is going to be the same as this angle. In fact, let me redraw this triangle out here. A little bigger so you can see it. So this is our weight, and this is our parallel weight, and this is our perpendicular. So, and this is 30 degrees, and this is a right angle. So to figure out, it wants to know the weight that's parallel. We're going to need to use a little bit of trigonometry, but we don't have numbers for these values, so we're just going to have to keep them as variables. So the sine of 30 degrees is going to be equal to the parallel weight over the total weight, because sine is opposite over hypotenuse. So the weight times the sine of 30 degrees is going to be equal to the parallel weight. And the sine of 30 degrees is 0.5, so 0.5 times the weight is going to be equal to the component of the weight that's going down the ramp. And that is going to be C. The next question is question 7, which says, in the diagram below, box M is on a frictionless table with forces F1 and F2 acting as shown. And it says the magnitude of F1 is greater than the magnitude of F2. The box is... Okay, so if this is greater than this, that means our net force, F net, is going to be equal to this force minus this force. So, because you always put the bigger one first to get a positive number, if that makes sense. So let's just give these numbers. Let's say this is 10 and this is 7. So our net force would be 3 in the same direction as F1. And since our net force is moving in the same direction as F1, it's going to be accelerating in the direction of F1, which is going to be A. The box is accelerating in the direction of F1 because the net force is in the direction of F1. Next question is question 8, which says, the diagram below represents a car standing on a hill. Which vector best represents the weight of the car? And the answer is going to be B, because the weight of any object, no matter what kind of slope or incline or whatever it's on, is always going to be perpendicular to the ground. So you always want to look for the vector that's perpendicular or at a right angle with the ground, and in this case that's going to be vector B. Question 9 says, a block rests on an inclined plane as shown in the diagram below. As angle theta is increased, the component of the block's weight parallel to the plane decreases, increases, or remains the same. So we looked at this a bit in question 6. So I'm going to draw you a few examples real quick. So, as you can see, as this angle, I probably should have drawn these in a different order. As the angle, it's small here, and the component of the weight, this vector that's parallel to the plane, is small. And then as the angle gets bigger, we have imagine these are all the same weight. I know they do look a little different. As the angle gets bigger, this component is going to increase. And then you can really see it as the angle gets really large. This component of the weight that's parallel to the plane gets very big. So as the angle increases, as this angle increases, the component of the weight parallel to the plane is going to increase. And another way to express that mathematically is because this component, the component of the weight that's parallel to the angle, or parallel to the plane, is going to be equal to the weight times the sine of the angle. And as the angle approaches 90 degrees, or as the angle gets bigger, the sine of the angle is going to keep increasing, and it's going to approach 1. So as theta goes from 0 degrees to 90 degrees, sine of theta goes from 0 to 1. So that is going to give us B. This is going to increase as theta increases. The next question is question 10, which says 4 forces are acting on an object as shown in the diagram below. If the object is moving with a constant velocity, the magnitude of the force F must be, hang on, let me draw this real quick. A key thing about this problem is that it says it's moving at a constant velocity. So v is a constant. Now we know that when something's moving at a constant velocity, our velocity versus time graph looks like this, which means that the acceleration is 0. So when our velocity is constant, our acceleration equals 0. And when you have an acceleration of 0, if you plug that into your net force equals your mass times your acceleration, you're going to get 0. Because no matter what the mass is, if you multiply it by 0, you're still going to get 0. So since this has a constant velocity, has 0 acceleration, and therefore has 0 net force, and that's something you're going to have to be able to pick up on in a problem. When it says something has a constant velocity, you can immediately go to assume that the net force is 0. You don't have to go and show this. So if our net force is 0, that means all these forces have to balance out. Now these are in opposite directions and they have the same magnitude, so these already cancel out. But F and this force of 40 newtons are in the opposite direction and they have to cancel out. So the force F has to equal 40 newtons. F equals 40 newtons, which is A. The next question is question 11, which says, the diagram below represents a force acting on point P. Which pair of concurrent forces would produce equilibrium when added to the force acting at point P? Okay, so producing equilibrium means there's no net force acting on the object. So equilibrium means F net equals 0. So for our net force to equal 0, we have to have forces canceling out this force. So if we split this force up into its component forces, we're going to get this and this. So now we need two forces acting in the opposite direction of these to cancel them out, which is going to look like this and this. Or, here, draw it separately. That and that, because this force cancels out this force and this force cancels out this force. And now if we go and look at our answers, that is A. The next question is question 12, and it says, which statement explains why a book resting on a table is in equilibrium? A, the weight of the book equals the weight of the table. No. I mean, could you not have a huge, like, 200 Newton table with a little comic book on it? And as long as that comic book's not moving, it has no net force acting on it. It's in equilibrium, so it's not A. B, the acceleration due to gravity is 9.8 meters per second for both the book and the table. Well, that's true, but that doesn't mean they're in equilibrium. And C says the weight of the book and the table's upward force on the book are equal in magnitude but opposite in direction. What they mean by this is, here you have your book on a table, and it's saying that the weight of the book, so this is weight of the book, down is equal to the force exerted by the table on the book, which is the normal force. So it's saying these two are equal but opposite in direction, and that's true. Whenever something is in equilibrium, that is by definition true. So C is the correct answer. Now let's just look at D. It says there is a net force acting downward on the book, and that's not true because it says that the book resting on the table is in equilibrium, and if it had a net force acting downwards on it, if it had a net force acting downwards, and it would be accelerating downwards. It would be like pushing down on the table, which doesn't make any sense. So it can't be D. It has to be C. The next question is question 13, which reads, which two graphs represent the motion of an object on which the net force is 0? Let me draw these real quick. Okay, so first of all, we can immediately cancel out B and C because these aren't even right. You can never, this speed is never going to represent that displacement, and that speed is never going to represent that displacement. If you don't understand that, I'm not going to explain it because it relates to the last chapter. Now, when net force equals 0, that means mass times net acceleration equals 0. And since mass is never going to be 0, that means your net acceleration has to be 0. Meaning that your velocity, or your speed, is going to be constant. So we have to look at which one of these has a constant speed, and it's D. The next question is question 14, which says the magnitude of the force that a baseball exerts on a bat is 50 newtons. The magnitude of the force that that the ball exerts on the bat is, and this is just a concept problem. If something's exerting a force on something else, that something else is exerting a force back on it. So if I push this hand with 5 newtons and this hand is pushing back with 5 newtons, otherwise I'd be pushing it away. So the answer is C, 50 newtons. Next question is 15, which reads, a box initially at rest on a level floor is being acted upon by a variable horizontal force as shown in the diagram below. Compared to the force required to start the box moving, the force required to keep it moving at a constant speed is greater, less, or the same. This is kind of a conceptual problem. So the reason that it takes more energy to start an object moving than to keep it moving, here, let me get an example object. Here's a stapler. Now if I push it just a little bit, it's not going to move, but then if I push it more and just keep pushing with less force, it is going to move. And the reason for that is that objects have friction, and there's two types of friction. There's kinetic friction and static friction. And static friction is always going to be greater than kinetic friction. What that means is it takes more force, it takes a greater force to move an object that's at rest than it is to continue moving an object once it's in motion. Because, yeah, the static friction is always greater than the kinetic friction. So in other words, there's less resisting force when an object's moving than when it's at rest. So the answer is going to be B. Next question is question 16, which says a cart is uniformly accelerating from rest. The net force acting on the cart is decreasing, 0, increasing, constant. So uniformly accelerating, uniform acceleration means that your acceleration is a constant. And when you have a constant acceleration, and F equals ma, then if you plug this into there, you're going to get your force equals your mass times some constant. So your force, and we have to assume your mass is constant, obviously, because it's just a cart. You're not assuming like there's this cart moving down the aisle and people are throwing stuff in it as it's going by. No, that's not going to work on a test. So this means that your net force is going to be constant because your acceleration is constant. So let's go over that again. Uniform acceleration means your acceleration is constant, means your net force is constant, which is D. Next question is question 17, which says a 5 kilogram cart moving with a velocity of 4 meters per second is brought to a stop in 2.0 seconds. The magnitude of the average force used to stop the cart is, ooh boy, now we're using kinematics and forces. Fun stuff. So first, let's write everything down. So we have our cart is 5.0 kilograms, which is our mass. We have an initial velocity of 4.0 meters per second. So it's brought to rest, which means our final velocity is 0 meters per second. And it's brought to rest in 2 seconds, which means our time is 2 seconds. So it wants to know the magnitude of the average force used to stop the cart. Okay, so we know that force equals mass times acceleration. And we have our mass, so we're looking for force. We have our mass times our acceleration. So to find our force, we need to find our acceleration. And to find our acceleration, we're going to have to use kinematics given this information. So what equation can we use that uses these three variables to find acceleration? We're going to use v final equals v initial plus at. So 0 equals 4 plus a times 2. So negative 4 meters per second equals our acceleration times our time divided by 2, and you get negative 2.0 equals our acceleration. We multiply that by our mass, and we get our force equals negative 10 newtons. But wait, that's not an answer. Okay, well, if we look back at the problem, it says it's asking for the magnitude of the average force, and magnitude is an absolute value. You're never going to have a negative magnitude. So we just go 10 newtons, which is C. The next question is question 18, which reads a 1.2 times 10 to the third kilogram automobile in motion strikes a 1.0 times 10 to the negative fourth kilogram insect. As a result, the insect is accelerated at a rate of 1.0 times 10 to the 2 meters per second squared. What is the magnitude of the force the insect exerts on the car? Wow. Okay, so let's start by drawing things. So we have our, first, question 18. We have our bug. And he's acted on by the force of the car. And it's asking for the force that he exerts back on the car. Well, we know they're going to be equal because they're a force pair. They're equal. Because, I mean, the car pushes on the bug and the bug pushes back on the car. It's kind of a weird concept, but you just kind of have to accept it, go with it. And to figure out this, we can look at the acceleration of the bug. Okay, so, sorry. We know that any force is going to be equal to some mass times some acceleration. And in this case, it's going to be equal to the acceleration of the bug times the mass of the bug. Sorry. We are looking for this force that the bug exerts on the car, which is the mass of the bug times the acceleration of the bug, which they give us. So it's just 1.0 times 10 to the negative fourth kilograms times 1.0 times 10 squared meters per second squared, which is going to equal 1.0 times 10 to the negative second newtons. Don't you love scientific notation? Which is going to be C. I don't like that problem. Let's move on. Question 19 says, a bird feeder with 2 birds has a total mass of 2 kilograms and is supported by a wire as shown in the diagram below. The force in the top wire is approximately... Hang on, let me draw this real quick. If you're expecting me to draw these 2 birds on there, you're insane. You've seen my drawing. It's terrible. So it's asking for the force of the top wire. This is a tension force, so we're actually going to call it T. That's the worst exclamation mark or question mark anyone has ever drawn. So we're looking for the tension in this wire. We know that this bird feeder is in equilibrium. So if we just draw it as a point particle, and we know that the force of gravity is equal to its mass times its acceleration, which we're just going to approximate to 10. So the force of gravity is 2 times 10, which is 20 newtons. So we know that the force pulling up on it is going to have to be equal to 20 newtons. F of x just kind of denotates some unknown force. But since these are in equilibrium, I mean, we're assuming that the bird feeder is not like breaking off. We're assuming it's just floating there. Not floating there, just hanging there. These two have to be equal. So our F of x is going to be equal to 20 newtons. Now we just have to figure out what's providing that 20 newtons of force. And yes, there's these 2 wires here, but ultimately it's only this wire that's holding it up. So the tension in the top wire is just going to be equal to 20 newtons, which is B. The next question is question 20, which says a 50 kilogram student standing on the earth attracts the earth with the force closest to, and this is another force pair question. So if you have your student, I'm just going to draw them as a point particle, with the Earth's gravity pulling down with a force of, let's see, 50 kilogram student. So force of gravity is mg, which is equal to 50 times gravity, which we're going to round to 10, so you're going to get 500 newtons. And since the student isn't moving, that means the normal force is going to be 500 newtons. And this is just another third law force pair. So the answer is going to be C. And it's a weird question. It's a weird concept, I mean, but you just kind of have to get familiar with it. Next question is question 21, which says each diagram below shows a different block being pushed by a force across the surface at a constant velocity. And it asks, in which two diagrams is the force of friction the same? So constant velocity, as I've said before, means our acceleration equals 0, which means your net force is going to be equal to 0. So that means the force of friction in each instance is going to be equal to the force acting on the block. And so you don't even need to look at what types of materials are. That's just there to trick you. You don't even need to look at the mass of the objects. That's just there to trick you. You just need to look at which two objects have the same force acting on them. Because if you have an object, let's look at A, with 2 newtons of force acting on it, and it's moving at a constant velocity, meaning its net force is 0, that means you have to have another force acting on it that's going to counteract this force. So you have to have another force acting in the opposite direction that's also 2 newtons. And when you add these together, you get a net force of 2 minus 2, which equals 0, which means it's either not moving at all or moving at a constant velocity. So you just have to look at A, B, C, and D and look at which two have the same force acting on it, because the frictional force is going to be the same as that force. And that's going to give you A and D, which is C. Next question is 22, which says a cart rolls down an inclined plane with a constant speed, as shown in the diagram below, which arrow represents the direction of the frictional force. Hang on, let me draw this real quick. Okay, so since it's moving down an inclined plane, that means its motion is downwards, and frictional force is always in the opposite direction of the motion. So in this case, So in this case, D is going to be your friction, because it's moving this way. Friction is opposing that motion, meaning friction is going up this way. However, if this cart or whatever it is were moving up the ramp, then A would be your friction, because A is the opposite. The vector A is in the opposite direction of the motion. And while we're here, I'm just going to tell you what each one of these 4 vectors actually are, just so you know. B, since it's perpendicular to the ground, is going to be your weight. The weight of your object. A is going to be the component of your weight down the ramp. C is going to be the component of your weight perpendicular to the ramp. And as we said, D is going to be your friction. So the answer is D. The next question is question 23, which says block A is pulled with a constant velocity up an incline as shown in the diagram below. Which arrow best represents, that's kind of hard to see, which arrow best represents the direction of the force acting on block A? So, direction of the frictional force acting on block A. Okay, as we just said, so here is our inclined plane, here's our block, and it's got a little pulley and another block, and it's moving this way. So the velocity is this way, meaning your motion is this way. And as I just said in the previous problem, the frictional force is always in the opposite direction of the motion. So our frictional force is going to be going this way. It's going to be our force of friction. And that is going to be, which answer is that? D. Because D is the only one that's remotely in the right direction. Next question is question 24, which says, a constant unbalanced force of friction acts on a 15 kilogram mass moving along a horizontal surface at 10 meters per second. If the mass is brought to rest in 1.5 seconds, what is the magnitude of the force of friction? Okay, so we have, let's write down all this information because they gave us a lot. So we have mass equals 15.0 kilograms. V initial equals 10 meters per second. And it's brought to rest, so that means our V final is 0 meters per second. And it's brought to rest in 1.5 seconds, so our time is 1.5 seconds. And it wants to know what is the magnitude of the force of friction. So, force of friction. So, to find our force of friction, we know that F equals ma. We know our mass. We're trying to find our force. So, we need to find A. So to find acceleration, there was another problem earlier like this. I can't remember which one it was. So to find acceleration, we need to use these three pieces of information, and we're going to use the equation. That was the worst arrow I have ever drawn. Oh man. So we're going to use V final equals V initial plus AT. So V final is 0. V initial is 10, acceleration is what we're looking for, and our time is 1.5 seconds. It's all given to you in the problem. So to find acceleration, subtract 10 over, then divide by 1.5. You get our acceleration, which is going to be negative 6.67 meters per second squared. And so that's our net acceleration on the object. In other words, this is the acceleration that the object has to have to change from a velocity of 10 meters per second to 0 meters per second in 1.5 seconds. But the problem is asking for the force of friction, which is the force that's going to cause the object to slow down. So to figure that out, we take our acceleration and multiply it by our mass. So we go back into here. So we're going to have our force of friction is going to be equal to our mass times negative 6.67. So that's going to be equal to negative 100 newtons, but it's asking for just the magnitude, so we get rid of that sign because magnitude is an absolute value, it's not a sign value. So it's just going to be 100 newtons, not negative 100, which is A. The next question is 25, which says the diagram below represents a 10.0 Newton block sliding down a 30-degree incline at a constant speed, and it wants to know the force of friction acting on the block is approximately. Hang on, let me draw this real quick. Okay, so here's what it gives you, and it wants to know the force of friction. And again, it says it's at a constant velocity, and when you have a constant velocity, it means your acceleration is 0. And if you plug A equals 0 into F equals ma, no matter what your mass is, your force, your net force is going to be 0, which means all the forces have to be balanced. So if we draw this again, with forces, we have, okay, so first, the only thing we know is we have the weight. It's a 10 Newton block. So this is 10 newtons downwards. And now we want to split that up into components that are parallel and perpendicular to the plane. So we have our force, our weight down the plane, and our weight perpendicular to the plane. And our weight down the plane is, let's see, it's going to be 10 sine 30, which is going to be 5 newtons. And our weight perpendicular to the plane is going to be 10 cosine 30, which is going to be 8.7 newtons. So now we need to, since it's at a constant velocity, our net force has to be 0, which means all these two forces have to be balanced. So the 8.7 newtons downward is going to be balanced by 8.7 newtons of normal force upwards, or perpendicular to the plane. And then the 5 newtons down the plane is going to be balanced by 5 newtons of friction up the plane. I hope you can see all that. I know it is a bit small. So And the question asks for the force of friction, which is just going to be this, 5.0 newtons. Which is D. So again, just to recap, it gave you the weight of the object, and it told you that it was moving at a constant velocity. When you have a constant velocity, that means your net force has to be 0. So then you have to look at this and say, okay, if this is my weight and it's sitting on a ramp, I have to balance this weight with forces that are going to give it a net force of 0. So you split up this weight into your parallel and perpendicular components of the weight, and then you balance the perpendicular component with the normal force, which is also perpendicular to the plane, which is kind of bowed because I can't draw, and you balance the downward component of the weight with the upward force of friction, and you get 5 newtons because they balance. The next question is question 26, which reads, a 100 Newton box rests on a horizontal surface. A force of 10 newtons parallel to the surface is required to start the box moving. What is the maximum coefficient of static friction between the box and the surface? Okay, so if we have our box, it weighs 100 newtons. That means it also has a normal force of 100 newtons. And it says 10 newtons parallel to the surface is required to start the box moving. What is the maximum coefficient of static friction? So that means our maximum static friction has to balance this force, because right as it starts moving is when the force required to start it moving is equal to the coefficient of static friction. So this, or not the coefficient of static friction, the force of static friction. So our force of static friction is going to be equal to our so our force of static friction is equal to our coefficient of static friction, which is denoted mu sub s. I should probably draw this bigger. So our force of static friction is equal to mu sub s times our normal force, and our normal force is just the same as our weight. So, and we know that our maximum force of static friction is 10 newtons, which is going to be equal to our mu sub s times our normal force, which is the same as our weight, which is 100 newtons. So divide that over, and we get our maximum coefficient of static friction is 0.1. The next question is question 27. Oh, and this is C. It's question 27, which says a horizontal force is used to pull a 5.0 kilogram cart at a constant speed of 5 meters per second across the floor, as shown in the diagram below. And it asks, is the force of friction between the if the force of friction between the cart and the floor is 10 newtons, the magnitude of the horizontal force along the handle of the cart is... Okay, so let me draw this real quick. We have our cart. Frictional force between the cart and the floor is 10 newtons, so it's being pulled backwards with a force of 10 newtons, and it's moving this way with some force that we don't know about. And it's moving... Oh, and it also weighs... Sorry, it has a mass of 5 kilograms. It does not weigh 5 kilograms. It weighs 50 newtons. Weight is in newtons, mass is in kilograms. Weight is not in kilograms. That's important to note. So it wants to know the magnitude of this horizontal force, F of x. And the way we figure that out is conceptually. We look at the cart and we say, okay, it's moving with a constant speed of 5 meters per second. We don't care that the speed is 5 meters per second. All we care about is that the speed is constant. So, as I've said several times before, when the velocity is constant, it means your acceleration is 0, which means your force, your net force, is 0, because F equals ma. And if you plug 0 into that, you're going to get your force equal to 0. So, since we know our net force is 0, we know that this force has to balance out this force, which means they have to be equal. So the force on the handle, the horizontal force on the handle, has to be 10 newtons, which is B. The next question is question 28. And it says, an object accelerates at 2.5 meters per second squared when an unbalanced force of 10 newtons acts on it. What is the mass of the object? So this is just a real simple F equals ma problem. You have an you have a known force of 10 newtons, you have an unknown mass, and you have a known acceleration of 2.5 meters per second squared. So you just divide it out. 2.5 equals our mass, which is going to be 4.0 kilograms, which is C. The next question is question 29 on the last page here, almost done. Question 29, which says, in the graph below, the acceleration of an object is plotted against the unbalanced force of an object, and it says, what is the object's mass? So you just look at any point on the graph, like let's say at the point where the force equals 2. So if we look at where the force equals 2, the acceleration is 4. So if we have force of 2 newtons and an acceleration of 4 meters per second squared, then we can figure out that our mass, relating them using F equals ma, Newton's second law, we can figure out that our mass divided over is 0.5 kilograms, which is A. Next question is question 30, which says an 800 Newton person is standing in an elevator. If the upward force of the elevator on the person is 600 newtons, the person is moving downward at a constant speed, accelerating downward at rest, or accelerating upward. Okay, so you want to draw a free body diagram. 800 Newton person. Okay, so that means their weight, their downward force due to gravity, is 800 newtons. And the upward force due to the elevator is 600 newtons. And if we add these together, or if we subtract them, I guess, which is our net force, and it is in the downward direction. So net force never goes on a free body diagram, but I'm just drawing it separately so you can see it. So our net force is moving downwards, and your acceleration, your net acceleration, is always in the direction of your net force. So your net acceleration is downwards. So just a quick recap on this problem. The person has a weight of 800 newtons, and the elevator is pushing up on them with a force of 600 newtons. So you find the difference between those, and that is your net force. And since the weight is greater than the force imparted by the elevator, the net force is downwards, meaning that the acceleration is downwards. So that's B. The next question is question 31. And it reads, two forces are applied to a 2.0 kilogram block on a frictionless horizontal surface as shown in the diagram below. And it wants to know the acceleration of the block. Hang on, let me draw this real quick. Okay, actually they draw it kind of misleadingly in the problem when I copied it, but your vector should match the magnitude of the force, so this should actually be like this, and that should be as it is. Because since this is only 2 newtons, it should be a lot shorter, it should have a smaller magnitude than the force with 8 newtons. And it wants to know the acceleration of the block. Okay, so to find the acceleration, you need to find the net force. So to find our net force, we're just going to take this force, which is what they call it, F2, and subtract this force, so F2 minus F1 equals our net force. Because remember, the net force is just the sum of all the forces acting on the object. So F2 is 8 minus F1 is 2 equals 6 newtons. And we know that the mass, so the force net equals your mass times your net acceleration. So your net force is 6 newtons, your mass is 2 kilograms, and your acceleration is unknown. So divide these over, and you get 6 over 2 equals 3 meters per second squared, which is A. Next question is question 32, which reads, as shown in the diagram below, an inflated balloon released from rest moves horizontally with velocity v. So we have a balloon that with air pushing this way, A-I-R, I know how to spell, and a velocity moving this way. It says the velocity of the balloon is most likely caused by, okay, so we're going to look at these 4 answers and eliminate the ones that don't make sense. First of all, A, rolling friction. We don't even know what that is, so that's wrong. C, centripetal force. Centripetal force causes things to move in a circle. The balloon's moving straight, so it's not C. B, action-reaction. Okay, that makes sense because the air is pushing this way, so it's going to be pushing backwards on the balloon, or the air is moving this way, so it's going to be pushing backwards on the balloon this way. And D, gravitational attraction. That would mean that everything's coming together, or that the balloon is moving downwards towards the Earth, and it's moving that way. So the answer is B, action-reaction, because the air is moving that way, so it's pushing backwards with the force that way. And the final question is question 33, which says a .025 kilogram bullet is fired from a rifle by an unbalanced force of 200 newtons. If the force acts on the bullet for 0.1 seconds, what is the maximum speed attained by the bullet? Okay, so we have a mass. We have our force. And we have a time. That's kind of weird. They gave us a time, says U. To figure out the maximum speed, or the maximum velocity, whatever you want to call it, we need to know the acceleration of the object. Well, they didn't give us the acceleration, but we know force and mass. And since F equals ma, we can plug everything in, divide it out, and you get your acceleration equals 8,000 meters per second squared. And we know that it accelerated for 0.1 seconds, and it wants to know the maximum speed, so it's looking for a velocity, and we know that our initial velocity is 0, so we're going to go v final equals v initial plus acceleration times time. So v final is what we're looking for, equals our initial velocity of 0 plus 8,000 times 0.1, and 8,000 times 0.1 is 800, so our final velocity is 800 meters per second, which is A. Thank you for watching this episode of PHS Physics SOS. If you have any questions, comments, concerns, leave them in the YouTube comments below or in the Facebook group, to which there is a link to in the description. If you're really struggling with this, contact me personally on Facebook, and I can help you one-on-one via Skype, or we can set up a time to tutor in person, like at school or after school or whatever. Because this is a difficult topic. This is a difficult chapter. Forces are, I mean, when you first start drawing free body diagrams, it's pretty complicated, especially with the stuff on the incline. It's like, whoa, what are we doing? So if that's really confusing you, just give me a holler. And thank you for watching. I hope you found this helpful.